Yeah, great. Thank you very much. Yeah, usually I prefer to get ill after conference. This time I managed to get ill just in time for my own talk. So in case I don't make all that much sense in the coming 15 minutes, I'll blame it on that. Yeah, but I hope we'll get through this. The starting point of this project was actually a talk by Pierre-Marie here in the first row last summer in Tallinn, who proposed that actually we can regard the dialectica translation for type theory as giving us a way to integrate quantitative or graded types, in case you've seen this before, into type theory. And not only was it very appealing to have a 100% free idea for a research project given for free to me, I was also kind of already thinking a bit about dialectica. I had the vague feeling that there was something interesting to be done because I talked to Valeria de Paiva earlier that year. Yeah, but Pierre-Marie had a clear idea what actually could be done. And this talk is kind of spelling this out and extending this. So we'll not actually really look at a translation. Yesterday we saw what the dialectica translation is. We rather take the dialectica translation as inspiration to come up with some form of linear dependent type theory. Yeah, one way to look at dialectica is that it linearizes an intuitionistic calculus, and we'll kind of take this perspective, but then really we don't translate any terms. We really just look at like some type system that comes out of something like dialectica. Yeah, so you will have to squint a bit maybe to convince yourself that this is actually dialectica, but I found, yeah, this way of setting things up useful. And as Pierre-Marie has already observed, is that this is actually giving us something quite cool, because in quantitative type theories, we will often have to over-approximate the multiplicity for some argument because we don't statically know how often some variable is used. In this dialectica approach, we can actually give some more fine-grained kinds of types. So we'll see examples of this. And what's cool about this approach is that we have all the structure available actually already in cubical acta with finite multisets. So you will also see some cubical acta code, and we can really play around with this linear type system already. Then the second half, if I get to that in that detail, is about extending this idea to have a really proper linear dependent type theory, because the first 3 points here, they will all not really have linear function types. Then the fourth point is about integrating linear function types. Yeah, without further ado, let's look at what I kind of understand as the dialectica translation, or what I found useful as a perspective on it. And that is the idea that if we want to linearize a function, so we kind of want to treat it in some resource relevant way, then we want to equip the output of this function with copies of the inputs, very, very roughly. We will use cubical acta's finite multisets to gather all kinds of inputs. So the supply you can think of as a maximally heterogeneous finite multiset. We can really put in any kind of value in our finite multiset. We have this double colon here for the con symbol, the diamond for nil. And of course, finite multiset is then also quotiented by reordering elements and set truncated. We will not really worry about this all that much. What we need to know is that our supplies have some way of concatenating to supplies. So this tensor here is kind of like list append, but it works out well with finite multisets because of all the work that has been done on higher inductive types. Then we'll just write this diamond as a set for the empty supply. And crucially, we can also take any kind of value A, which is of some type A, as a unit supply. So we just embed this as a supply by putting it in front of the empty supply. So this is all just basic cubical acta. What I think is the main idea that is relevant to us is really that we equip the output type of a function with copies of the inputs, I said. And for this, we introduced this dependent type here. So our delta is meant to be some supply, some multiset of resources. And we say that from this finite multiset of resources, we can derive something of type A if we can actually obtain something of that type. And kind of, we'll spell out what this quotation marks equal sign means here. Kind of morally, the supply and this element A that we constructed are equal from the perspective of resources. So that's the basic setup. So if we look at a example program, so that's just a basic ACTA program which wants to extract the head of a list, but in case this fails, gets a backup element y. To now treat this in a resource relevant way, we annotate the output of this function type with copies of the input. So we construct this supply here, which is actually a program which gives us supplies, which we would expect should give the correct type for this program, because our y here is only used in case that our first given element, so this list is empty. So only in case null access evaluates to true, we actually do want to consume a y, and otherwise we don't need anything at all. But we'll always need to use the list access. And since this is just a sigma type, this linear derivation predicate, really we can still have our same intuitionistic terms here for the program. And now we have to satisfy these proof goals. And if we look at these proof goals, they're kind of like I said, we understand this quotation marks equal as morally it's the same resources. And I mean, having a y in an empty list kind of is the same as having a y, comma, the empty list. And also here, having just the diamond and then x cons axis is kind of the same as having x, comma, axis, right? So this is something that we want to capture. Like, in which way do we really consider two supplies to be equal? And for this purpose, we introduced this data type, which if you have experience with symmetric or with monoidal categories, you will already kind of see where this is getting at. It kind of is just about giving us some way of relating to supplies where we can relate supplies also if they're not like equal as far as cubical acta is concerned. So the first three constructors are actually something that would also hold for inequality. The interesting ones are really this OPL, stands for oplux and lux, where kind of this means opl, comma, takes this supply and produces this supply on the right-hand side, whereas lux, comma, goes the other way around. So it's a succinct way to write two constructors, really. And what they say is really, well, if I have an A, comma, B, I can also just treat A and B separately. Or if I have an empty list, I can just discard it. And if we go the other way around, we can just, always introduce an empty list. And also similarly for the cons operator. And using this production data type, I call it, we will now really define our linear derivability predicate. And this will just say, uses this production data type as a relation between the supply and the unit A supply. And using this, we can now program. So going back to our safe head function, if we look at the proof goals, now we have these triangles here, we can really just look at the constructors of our productions to resolve these proof goals. So here, for instance, we would just have to say, well, we need to kind of put a comma in between this y and the empty list here. So this will resolve our proof goal. Here, we have to get rid of a cons and introduce a comma. So it's actually the composition of two of these productions. But this is all kind of just plain cubical acta, and you can program in it, and you actually find out, if you maybe did a wrong resource annotation, that really you won't be able to derive these productions. What's cool about this, I think, is that we so far had only had to talk about constructors, right? We introduced some cases for the constructors for these data types that we care about. We never had to say anything about elimination principles, right? So starting with Conor McBride, there's been kind of work on what does it mean to eliminate a quantitative data type. We don't have to stipulate anything at all in our system, but rather we can derive these linear elimination principles. So for instance, if we have a fold R for our list, which kind of says we have a recursive case where we use the kind of currently produced result of type B and the current head of the list X and some supply delta 1 to create a B, and we have some base case which uses another supply to create a B. Then applying this to a list, we can actually really find out, okay, we will need to have delta 0 and as many copies of delta 1 as we have elements in the list, where this caret symbol is, again, also just defined in plain cubical acta, right? So a finite multiset, we can just take m copies of by just, this recursive function. So in this way, we do not only kind of get elimination principles for free, and we know that they are right, because like in the definition of fold R, you will have to derive the appropriate productions. They're also very general, right? Because I mean, here we did some computation checking what the first value is. Here, we really compute the length of some list to find out how many copies of this specific supply we need. So it's a very general system, and yeah, it allows us to give quite specific resource annotations. Yeah, so you can write sorting programs in this relatively easily. It's really kind of always the same programs. You just have to also come up with these reductions. And of course, if you introduce a new data type, you also have to extend this reduction data type. Okay, so this for the first half of this talk. That's kind of neat. We can just program in the system cubical acta. We didn't have to make any changes to a type theory or anything like this. But I think it's good to kind of take a step back, see what we actually did independently of cubical acta. And then this will also give us an idea how we can turn this into a full dependent linear type theory. What we did is actually relatively straightforward. If we have some dependent type theory, this is not going to turn into a semantics talk. So we'll just say we have a category of context and the morphisms are substitutions. And we'll have types and terms. The only thing we care about is this term. So it's a brief sheaf. It assigns to any context just a set of terms in some way. Then this basically dependent type theory, we extend it by also giving this supply pre-sheaf, which now is not valued in sets, but in these symmetric model categories, right? So at each context, we have a symmetric model category. And also we were able to introduce things into our supplies using just some basic terms. So really, we have this natural transformation between the term and supply functors, which allows us to embed terms of the basic language. And then to take into account these positive types, really what we just had is that this iota is strongly monoidal. So it doesn't matter if we have a const or a tensor. These are really isomorphic objects in our symmetric model categories. So this is kind of all we did. And you can also add this to other languages by maybe making a bit more explicit the structure and not having a finite multiset which computes. But yeah, you can still kind of embed this into an existing dependent type theory without hits, which is neat. But now for the last 2 minutes, I think I would also like to talk a bit about the dependent linear functions that we wanted to introduce. How I would like to think about this way of combining linear and dependent types is really that we have a two-step calculus. We kind of have our intuitionistic set of variables gamma, and then we have our delta, which is not a list of variables, but it's really kind of taking things from the gamma. But it provides us with some sort of context in quotation marks that we need to use to produce something of type A. So it's really this two-step thing where actually this derivability predicate is just a certain dependent type that we can define using this structure above. But yeah, this perspective allows us to think about dependent function types, what they should look like. And I think this very sketchy semantics also suggests how we can add dependent function types, because if we have a symmetric monodic category here, we probably want to close this to be able to talk about function types. So that's what we're going to do. Actually, we find out, I think I need to close, that this is not quite enough. So we do not only need to have these exponential objects in each supply gamma, we also have to have some variable binding principle. We'll see how this comes into effect in a second, which I think is actually also a quite natural thing to add. We kind of have at our dependent type theory at every context a linear world, and dependent type theory has this context extension morphism P kind of as the central structural rule. And we have to, in some way, talk about this P, how we relate to it. And actually, we just need a writer joint to this for our supplies. And in that way, we then are able to derive our function types. So these are the function types. Very briefly, they're kind of just pairs of usual dependent functions, and then a supply which establishes that we need exactly an input to produce an output. So this is something we can define with using our exponentials and our variable binding principle. And then, yeah, we actually are able to derive, again, using this structure, something which is nice to use. So for instance, this introduction principle for functions, we just say, okay, if we have a gamma and an x in our context, then if we have a single copy of x and some other supply which doesn't mention x, and we can derive a b, well, then we should be able to form a dependent linear function. And we can actually do this using this structure. And this generalizes also to these multiplicities that are defined kind of over the natural numbers. And then we can really internalize this safe head function, which previously was just some relatively obscure cubical actor code. We really get a function in the system that says, well, the first list we'll use once. The second element, this should be in Y only, not YS, we'll only have in case that axis is null. And using this, we linearly produce this pair. So this works, and it's neat, I think. And yeah, many thanks to many people I talked to along the way. This first link here is the cubical actor code, so you can play around with this. This is relatively mature. The right side, the LTT is still very experimental, so this is where I try to implement the second half of this stuff using really the linear dependent functions. Yeah, thanks.